Welcome! In this session, we will dive into LeetCode problem number 1987, titled Number of Unique Good Subsequences. This is an exciting and challenging problem that involves counting unique good subsequences in a binary string. We'll explore different approaches to solve it, discuss its complexity, and highlight key concepts along the way. Let's get started. In this problem, we are working with a binary string, which is a string composed of only the characters 0 and 1. A subsequence of a string is formed by removing some characters, possibly none, while maintaining the order of the remaining characters. For example, from the string 001, we could form subsequences like 0, 01, or 001. Now, a good subsequence is specifically defined as one that starts with the character 1. So, subsequences that begin with 0 do not qualify. The goal is to determine how many unique good subsequences can be generated from the given binary string. Since the number of subsequences can grow very large, the result should be returned modulo 10 to the power of 9 plus 7. Let's look at an example to understand the task better. Suppose the input binary string is 001. The unique good subsequences here are 1 and 01. Notice that both of these subsequences start with 1, fulfilling the requirement of being good subsequences, and each subsequence is distinct. So, the output for this input is 2. In another example, if the input is 11, the unique good subsequences are 1 from the first occurrence, 1 from the second occurrence, and 11. However, since duplicates are not allowed, we count only the distinct ones, which are 1 and 11. This gives us an output of 3. Now consider the example where the binary string is 101. Here, the unique good subsequences are 1, the second occurrence of 1, 10, 01, and 101. Again, all of these start with 1, making them good subsequences. This gives us a total of 5 unique good subsequences. Moving on to the constraints, the length of the binary string can go up to 10 to the power of 5, which means we need an efficient approach to solve this problem. Additionally, the modulo operation ensures that the result remains within manageable limits, specifically under 10 to the power of 9 plus 7. It's also important to remember that only subsequences starting with 1 are considered valid for this problem. To solve the problem of counting unique good subsequences in a binary string, we first need to understand what makes a subsequence good. A good subsequence is non-empty and does not start with 0, unless it is the single character 0 itself. The challenge here is to count these subsequences efficiently, with the result being taken modulo 10 to the power of 9 plus 7. One approach we can consider is brute force. This involves generating all possible subsequences of the binary string, filtering out the invalid ones, and then ensuring the remaining subsequences are unique. While conceptually straightforward, this method quickly becomes computationally expensive as the number of subsequences grows exponentially with the length of the string. For example, for a string of length n, there are 2 to the power of n possible subsequences, which is infeasible for larger values of n, such as n greater than 20. This makes brute force impractical for solving the problem efficiently on larger inputs. Instead, we need a more optimized approach, such as dynamic programming, which we will explore next. A dynamic programming approach allows us to count unique good subsequences efficiently by leveraging observations about their structure. First, note that good subsequences either start with 1 or are the single character 0. To track subsequences dynamically, we can maintain 2 variables, one for the count of subsequences ending with 0, and another for those ending with 1. As we iterate through the binary string, when we encounter a 1, it can be added to all subsequences ending with either 0 or 1, or it can act as a new standalone subsequence. On the other hand, when we encounter a 0, it can only be added to subsequences ending with 1. Additionally, we track whether the string contains at least one 0, as that allows us to include the standalone 0 in our final count. Using modular arithmetic ensures that our counts do not exceed the problem's constraints. The implementation captures this logic in a highly efficient way, iterating through the string and updating the counts dynamically. This avoids the need to explicitly generate subsequences, making the solution scalable. The dynamic programming approach has a time complexity of O, n, and a space complexity of O, 1, where n is the length of the binary string. This makes it highly efficient, even for large input sizes. The trade-offs here are clear. While brute force is conceptually simpler, its exponential complexity renders it unusable for larger strings. In contrast, dynamic programming requires a deeper understanding of the problem but delivers an optimal balance between efficiency and simplicity. By categorizing good subsequences into those ending with 0 and 1, and updating counts dynamically as we iterate through the string, we ensure correctness and scalability. Additionally, using modular arithmetic allows us to handle the large output size without issues. This makes the dynamic programming method the most effective strategy for this problem. It is well suited to handle edge cases, such as strings composed entirely of zeros or ones, and ensures the solution is both optimal and practical for competitive programming scenarios. To solve the problem of counting unique good subsequences, we adopt a dynamic programming approach that efficiently handles the constraints and complexity. First, let's understand the problem requirements. We are working with a binary string, where each character is either 0 or 1. A good subsequence is defined as a non-empty subsequence that does not start with 0, unless the entire subsequence itself is 0. Our goal is to determine the number of unique good subsequences, taking the result modulo 10 to the power of 9 plus 7. Now, to break this down, we start by observing that any subsequence can be formed by including or excluding characters from the string, which generally leads to an exponential number of possibilities. However, to focus on unique good subsequences, we strategically track subsequences that end with 0 or 1 separately. If the string contains the character 0, we also include the single subsequence 0 as a valid result. To implement this efficiently, we define two dynamic programming variables, dp0 and dp1. Here, dp1 counts the unique good subsequences ending with 1. On the other hand, dp0 tracks the count of unique good subsequences ending with 0. By using these variables, we can avoid redundant calculations and ensure that the process runs efficiently in linear time. The next step involves iterating through the string. For each character in the binary string, we update these variables based on whether we encounter a 1 or a 0. If the current character is 1, we update dp1 by adding the previous count of subsequences ending with 1, the new subsequences formed by appending 1 to those ending with 0, and the single character subsequence 1. If the character is 0, we update dp0 by adding the previous count of subsequences ending with 0, as well as new subsequences formed by appending 0 to those ending with 1. To handle large numbers and prevent overflow, we apply modulo 10 to the power of 9 plus 7 after each update. Lastly, we account for the special case where the string contains 0. If it does, we add the single subsequence 0 to the result. Now, why do we use dynamic programming here? Instead of explicitly generating all possible subsequences, which would be computationally expensive for large strings, we use dp0 and dp1 to efficiently track the counts of unique good subsequences. This reduces the problem's complexity from exponential to linear. Modulo arithmetic is incorporated throughout the process to ensure correctness and prevent overflow, as the result needs to be taken modulo 10 to the power of 9 plus 7. Furthermore, we carefully handle edge cases to ensure valid subsequences starting with 0 are included when appropriate. For instance, the single character subsequence 0 is explicitly checked and added if the string contains 0. In terms of data structures, we use just two integer variables, dp0 and dp1, to minimize memory usage while enabling efficient computation. Together, these techniques allow us to strike a balance between efficiency and correctness. The time complexity of this approach is linear, O(n), where n is the length of the binary string. The space complexity is constant, O(1), since we only use two variables to store intermediate results. Now, let's summarize the final algorithm. We initialize dp0 and dp1 to 0 and use a flag called has_0 to track whether the string contains the character 0. As we iterate through the string, we update dp0 and dp1 based on the logic we discussed earlier, applying modulo 10 to the power of 9 plus 7 at every step. After completing the iteration, the result is obtained by summing dp0 and dp1, again modulo 10 to the power of 9 plus 7. If has_0 is true, we add 1 to the result to account for the single character subsequence 0. This approach ensures that we calculate the total number of unique good subsequences efficiently and correctly. Here's the Python implementation of the algorithm, which translates these steps directly into code. By following this logic, we achieve an optimal solution to the problem. This Python implementation solves the LeetCode problem number of unique good subsequences using a dynamic programming approach. Let's walk through the code step by step. 1. Initialization. We define a large constant mod equals 10 to the power of 9 plus 7 to handle the modulo operation, as the result can grow large. We also initialize two variables, count underscore ends underscore with underscore 0 and count underscore ends underscore with underscore 1, to track the number of unique good subsequences ending with 0 and 1, respectively. Additionally, we use the has underscore 0 flag to check if the binary string contains a 0. 2. Iterating through the string, we loop through each character in the binary string. If the character is 0, we update count underscore ends underscore with underscore 0 by adding count underscore ends underscore with underscore 1 to it. This is because any subsequence that ends with 1 can have 0 appended to it to create a new subsequence. We also set has underscore 0 to true to account for the standalone 0 as a good subsequence. If the character is 1, we update count underscore ends underscore with underscore 1. In this case, any subsequence that ends with 0 or 1 can have 1 appended to it to form a new subsequence. Additionally, the standalone 1 itself is a valid subsequence, so we add 1. 3. Final calculation. After processing the entire string, the total number of unique good subsequences is the sum of count underscore ends underscore with underscore 0 and count underscore ends underscore with underscore 1. If the binary string contains 0, we add 1 to account for the subsequence 0. Finally, we return the result modulo 10 (9 plus 7. This approach ensures that we efficiently count all unique good subsequences in linear time, (n), where n is the length of the binary string. It also handles edge cases like strings containing only zeros or ones seamlessly. This is the Java implementation of LeetCode problem number 1987, number of unique good subsequences. The logic mirrors the Python solution, using variables to track subsequences ending in 0 and 1, with a flag to account for standalone 0. Java-specific differences include explicit type declarations and modular arithmetic with long types. The function calculates the result iteratively while processing the binary string. To solve this problem, we start with the input string 101. First, we initialize our variables. The modulus constant, mod, is set to 10 to the power of 9 plus 7 to handle large numbers. We also initialize two counters, count underscore ends underscore with underscore 0 and count underscore ends underscore with underscore 1, both set to 0. These will track the number of good subsequences ending in 0 and 1, respectively. Additionally, a Boolean flag, has underscore 0, is set to false to track if the string contains at least one 0. Now, as we process the string, the first character is 1. Here, we update count underscore ends underscore with underscore 1 using the formula, the sum of count underscore ends underscore with underscore 0, count underscore ends underscore with underscore 1, and 1, all modulo mod. Substituting the initial values, this update gives us count underscore ends underscore with underscore 1 equal to 1. Moving to the next character, 0, we update count underscore ends underscore with underscore 0 as the sum of count underscore ends underscore with underscore 0 and count underscore ends underscore with underscore 1, modulo mod. This evaluates to 1. At the same time, we set has underscore 0 to true because we encountered a 0. Finally, processing the last character, another 1, we again update count underscore ends underscore with underscore 1 based on the formula, which we'll calculate next. Here, for the last one, count underscore ends underscore with underscore 1 is updated using the formula, count underscore ends underscore with underscore 0 plus count underscore ends underscore with underscore 1 plus 1, all modulo mod. Substituting the current values, this becomes 1 plus 1 plus 1 modulo mod, which equals 3. With the string fully processed, we calculate the result. The result is the sum of count underscore ends underscore with underscore 0, count underscore ends underscore with underscore 1, and an additional 1 if has underscore 0 is true, all modulo mod. In this case, the calculation is 1 plus 3 plus 1 modulo mod, resulting in 5. Therefore, the output for the input 101 is 5. Now consider the second example with the input string 0. Again, we initialize our variables. Mod is set to 10 to the power of 9 plus 7, count underscore ends underscore with underscore 0, and count underscore ends underscore with underscore 1 are both set to 0, and has underscore 0 is set to false. Processing the single character, 0, we update count underscore ends underscore with underscore 0 as the sum of count underscore ends underscore with underscore 0 and count underscore ends underscore with underscore 1, modulo mod. Since both counters are initially 0, this calculation results in count underscore ends underscore with underscore 0 remaining 0. However, we set has underscore 0 to true since we encountered a 0. With the string processed, we calculate the result. Using the formula, the result is the sum of count underscore ends underscore with underscore 0, count underscore ends underscore with underscore 1, and an additional one if has underscore 0 is true, all modulo mod. Here, the calculation becomes 0 plus 1 modulo mod, which equals 1. Thus, the output for the input 0 is 1. For a third example, consider the input 111. The initialization remains the same, mod is 10 to the power of 9 plus 7, count underscore ends underscore with underscore 0, and count underscore ends underscore with underscore 1 are set to 0, and has underscore 0 is false. Processing the string 111, the first character is 1. Using the update formula, count underscore ends underscore with underscore 1 becomes 0 plus 1 modulo mod, which equals 1. For the second one, count underscore ends underscore with underscore 1 is updated again, now as 0 plus 1 modulo mod, giving 2. Finally, for the last one, count underscore ends underscore with underscore 1 becomes 0 plus 2 1 modulo mod, resulting in 3. Now, we calculate the result. Since there are no zeros, has underscore 0 remains false. The result is the sum of count underscore ends underscore with underscore 0, count underscore ends underscore with underscore 1, and 0, all modulo mod. This evaluates to 0 plus 3 plus 0 modulo mod, which equals 3. Therefore, the output for the input 111 is 3. Here, we analyze the time complexity of the solution. The algorithm processes the input string, binary, in a single pass, where n is the length of the string. It iterates through each character exactly once using a for loop, contributing n to the time complexity. Within each iteration, all operations are constant time. For instance, checking whether the current character is 0 or 1 takes 1, updating the counts count underscore ends underscore with underscore 0 and count underscore ends underscore with underscore 1 is also 1, performing the modulo operation with mod is 1, and updating the has underscore 0 flag is 1. Since all these operations are constant, the overall time complexity is n, driven entirely by the single pass through the string. Now, let's look at the space complexity. The algorithm only uses a few integer variables to store intermediate results. Specifically, count underscore ends underscore with underscore 0, count underscore ends underscore with underscore 1, and has underscore 0 each require constant space, or 1. Additionally, no extra data structures are used, and there are no recursive calls, meaning the space usage is independent of the size of the input. Therefore, the overall space complexity is 1, making this an extremely memory-efficient solution. Next, we consider the best, average, and worst cases for the algorithm. In the best case, where the input string is very short, such as a single character, the algorithm still processes the string in n time, but the absolute runtime is minimal due to the small value of n. In the average case, for strings of moderate length, the algorithm remains n, as it always processes each character once. In the worst case, when the input string is very long, the algorithm still runs in n time, regardless of the string's content. Comparing this to a brute force or naive approach highlights the efficiency of the current solution. A naive approach would involve generating all subsequences of the binary string, which results in 2 to the power of n subsequences for a string of length n. Checking each subsequence for uniqueness and goodness would further increase the runtime, leading to a time complexity of 2 to the power of n, which is infeasible for large inputs. The naive approach, with its exponential time complexity of 2 to the power of n, is not practical for large inputs. Additionally, the space complexity would grow significantly due to the storage of all subsequences. In contrast, the optimized approach avoids generating subsequences entirely. By using dynamic programming and maintaining two counters to track subsequences ending with 0 and 1, the solution reduces the time complexity to O, n, and the space complexity to O, 1. This makes it both efficient and scalable. Mathematically, the big O analysis confirms this. The for loop iterates exactly n times, contributing O, n, and each operation within the loop is constant time, or O, 1. Multiplying these together gives an overall time complexity of O, n. The space complexity remains O, 1, as no additional memory is used beyond the few integer variables. This ensures the algorithm is optimal in both time and space usage. When solving this problem, there are a few common mistakes to watch out for. The first is ignoring subsequences that start with 0. It might seem like sequences like 01 foot or 001 are valid good subsequences, but that's incorrect. A subsequence starting with 0 is only valid if it is exactly 0. Any other subsequences starting with 0, such as 2000 or 001, are not valid. Next, another common mistake is overcounting duplicate subsequences. Many solutions accidentally count the same good subsequence multiple times because duplicates in the string aren't properly handled. To avoid this, you can use techniques like maintaining a set or leveraging bitmasking to ensure only unique subsequences are considered. Lastly, edge cases are often misinterpreted. For example, strings like 0, 1, or those with only repeated zeros, such as 000, need special attention. While a single 0 is valid, repeated zeros don't add to the count because they don't create new unique subsequences. Proper handling of these cases ensures your solution is accurate and robust. Now, another pitfall to avoid is relying on an inefficient brute force solution. Generating all possible subsequences and checking each one is highly impractical, especially for large strings. This approach has exponential time complexity, specifically O, 2 to the power of n, which makes it infeasible for inputs as large as 10 to the power of 5. Instead, you'll need to use more efficient strategies. Additionally, improper handling of leading zeros is another frequent issue. While 0 is a valid subsequence, invalid ones like 2000 or 000 should not contribute to the count. Mismanaging this distinction can lead to overcounting or incorrect results. Ensuring that your implementation correctly distinguishes between valid and invalid subsequences is key to solving this problem effectively. This problem is often used in interviews to assess your understanding of dynamic programming and pattern recognition. The core idea is to recognize that this is a variation of counting unique subsequences, a common dynamic programming pattern. The challenge lies in handling constraints like leading zeros appropriately. Using DP to track counts for subsequences ending in 0 and 1 is an efficient approach. For example, maintaining variables like count_0 and count_1 simplifies the state transitions needed to calculate the result. It's also important to be aware of edge cases, as interviewers frequently test inputs like 0, 1, or 10, as well as large strings of size up to 10 to the power of 5. A generalized solution that handles both small and large cases will demonstrate your thorough understanding. Additionally, discussing space optimization, such as reducing from O, n, to O, 1, using rolling variables, can showcase your ability to refine solutions. Finally, you might want to touch on how these patterns can be applied to real-world problems involving sequences, binary strings, or other unique constraints, as this illustrates the broader relevance of your approach. If you're looking to strengthen your understanding of this problem, exploring related problems can be incredibly helpful. For instance, LeetCode 940, Distinct Subsequences 2, focuses on counting distinct subsequences in a string, which directly complements the concepts here. Another problem, LeetCode 115, Distinct Subsequences, asks you to find how many times one string appears as a subsequence in another, reinforcing your ability to manage subsequences under different constraints. LeetCode 1937, Maximum Number of Points with Cost, is another dynamic programming problem that involves working with constraints, which can help you see parallels in how DP is applied across various contexts. Lastly, LeetCode 1044, Longest Duplicate Substring, focuses on string manipulation and identifying uniqueness, which ties into the skills needed for this problem. Practicing these problems can deepen your understanding of dynamic programming and string manipulation techniques. There are several approaches to solving this problem, each with its own trade-offs. One option is to use hashing combined with sets to store all unique good subsequences. While this is straightforward to implement, it can have a worst-case complexity of O(n) squared due to repeated checks, making it inefficient for large inputs. A more efficient and preferred approach is dynamic programming. By maintaining two counters, count_0 for subsequences ending in 0 and count_1 for those ending in 1, you can achieve O(n) time complexity and reduce space usage to O(1) by using rolling variables. Modular arithmetic ensures you avoid overflow when working with large numbers. Another method is bit masking, where you represent subsequences using bit operations. However, this becomes computationally expensive for long strings, so it's only practical for small inputs. Finally, you could use recursion with memoization to explore all valid subsequences. While this approach is often cleaner to implement, it's generally less efficient than iterative DP for large-scale problems. Choosing the right approach depends on the input size and the specific constraints of your implementation. That wraps up our discussion of LeetCode problem number 1987, number of unique good subsequences. We summarized the key steps, time and space complexities, and major takeaways from this problem. Remember, dynamic programming is a crucial tool for these types of challenges. Thanks for tuning in, and don't forget to like, share, and subscribe to stay updated with more problem-solving guides. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!